Thank you everyone for joining the session. Today we will be talking on this particular topic called fission and fusion technology in net zero carbon. My name is Vinay Karnam, and down the presentation, I'll give a brief introduction of myself and take you through the topic. Feel free to drop in questions in Q&A section, like Holly mentioned. All right. We'll go from here. So a brief disclaimer, all the opinions expressed in this presentation are personal and do not represent the views of Special Interest Group for Immigrant Engineers or Engineering New Zealand, for that matter, any other organization, all right? The data shown in this presentation is for illustration purposes only, and the presenter do not take any responsibility about its accuracy. The concepts may be may not be in exact definition and have been oversimplified for illustration purposes. What do I mean by this? Is let's say if you're looking at the definition of joule, okay, which is a measurement unit of energy. Okay, we are talking about energy here, but energy is basically in joule, power is in watts, but we will not be talking in terms of joule second or joule hour. We'll be talking mostly we'll be talking mostly in terms of joules or kilowatts. Okay, so that way the units may be interchangeably used. Okay, we'll not go by the exact definition, like work done, which is a dot product of force and distance. Okay, so we will not go by the exact definition. Hope this is all right. We'll go to the next one. What are we discussing today? We will be discussing the introduction to fission and fusion. What are they? How do they work? And what are the spin-offs of this technology that the world is leveraging in day-to-day activities? Then relevance of these technologies in the space of climate change response, right? And then we will look at the big picture at the end. A brief introduction about myself. I'm an immigrant mechanical engineer. Since I graduated in 2008, I have been working in the area of energy security. In January 2020, I immigrated to New Zealand. Since then, I have been pursuing dual career in information system and also in net zero carbon energy solutions, right? The reason I chose this area of energy security after my graduation is that I believe that the participation of engineers in infrastructure rather than information is very important, so that we directly contribute to the gross domestic product, GDP, because GDP and energy security go hand in hand. They have a very strong correlation. You take care of energy security, the GDP of the nation goes up. All right. So this is very important from that perspective. And I chose this career among many options, quite lucrative options, especially from the information systems, information technology careers. But I thought it is my ethical obligation to serve in mechanical engineering department to take care of the energy security needs. Right. Let's move on. So what is fission and fusion? Fission is a physical process through which tremendous amount of energy, almost 1 million times more than coal, okay, this is weight-to-weight basis, is released by splitting a large atom, specifically unstable atom, into smaller stable atoms. That's fission, okay? So typically, a large atom, a very big atom, okay, that is split, and during the process of splitting, a tremendous amount of energy is released that we would make use of, right? And how it is different from fusion? Fusion is a process where, again, tremendous amount of energy is released during the process, and the process is of joining two lighter elements into a larger one, all right? Just the opposite of fission, okay? In fission, we split the large atom into smaller ones. In fusion, we fuse, we join two lighter atoms into a larger one. In both the cases, tremendous amount of energy is produced. Fusion, by far, is only practical energy system available, which is the highest, Fusion, the energy released in fusion is almost 4 times that of fission. And we have seen in the previous slide that fission produces almost 1 million times the energy compared to, let's say, each gram of carbon that a coal can produce, okay? So that makes fission and fusion technology very relevant and very attractive for the energy engineers and energy scientists as a great source of energy. One of the things I would like to highlight is that if you ask even a primary school student, what is the ultimate source of energy on Earth? And promptly, the child replies that it is the sun, okay? But we fail to look beyond this answer, that sun is a natural nuclear reactor, a fusion reactor. And so conclusively, the ultimate source of energy on Earth is basically nuclear, all right? So nuclear energy is the ultimate source of energy on Earth and probably in this entire universe, right? There are certain conceptual ideas that of antiparticle reactors and so on, but they are yet to be proven experimentally, demonstrated experimentally. They are either too expensive to reduce the antiparticles and use them for producing energy and all that. The net energy produced by the system sometimes, or most of the times so far, has been negative. So it consumes more energy than produced, okay? So with all that information, so fusion is the only available practical solution, which is the largest source of energy weight basis. And fusion is yet to be commercialized. So by all practical purposes, established technology, which is the greatest source of energy today on Earth, is fission, okay? Let's move forward. Let's talk of fundamentals of fission before we talk about how the layout of the plant looks from engineering point of view, and also the working of it, and what are the different types of reactors. Let's understand some fundamental concepts here, okay? The fundamental concept in nuclear engineering rests on the concept called binding energy. What is binding energy? Binding energy is basically the energy required to separate one associative particle from the system, nucleus, or energy required to break that nucleus, okay? That's called binding energy, okay? Like the name implies, in mechanical engineering, everything is quite logical, okay? The name explains everything. So binding energy is the energy required to bind the nucleus together, all right? So nucleus, which is a Latin word, nuke, which means inner core, okay? Which is in the center of the atom, all right? This nucleus typically contains neutrons and protons for all practical. Like I have told in the beginning, I'm oversimplifying the mathematics of it, okay? So when I say neutrons and protons, when we are talking about constituents of a nucleus, probably, you know, it's a one-day discussion that we can have, and it will still be inconclusive and debatable, okay? I'm oversimplifying the concept here that nucleus contains neutrons and protons, and they are held together by a very strong nuclear force, probably the strongest force known to mankind, all right, at the atomic level. So these nuclear forces are opposed through Coulombic forces. You know, there is a Coulombic forces, basically electrostatic repulsion between protons, you know, because they are equally charged. All right. So this is how the energy is required to split or break this nucleus, okay? So this binding energy is by definition equal to the amount of energy required for removing one particular constituent from the system or break the entire system into individual constituents, okay? Mathematically, they are same. So this binding energy is what results in the thermal energy. It's exothermic process, okay? So when we split a large atom, it breaks into smaller fragments, okay? Multiple fragments. It may not be two. It is basically quite a probabilistic distribution you have. You get all kinds of elements ranging from hydrogen to americium. So you get all kinds of elements, okay? So there is a probabilistic distribution. So these elements, when produced, if you weigh the mass of the resultant fission products, okay, or the fragments, that will be lesser than the starting larger atom. And this difference in mass, okay, results in this tremendous amount of energy, okay? Binding energy is equal to delta M times C square, okay? This delta M, that is missing mass, okay, times the C square, speed of light, C square, is delta E, which is binding energy. All right. So this is how, this is the basis of working of nuclear power plants, right? Let's understand what is fissile and what is fertile material, okay? Fissile material is something which can be split easily and directly, okay? So fissile material is a very good fuel for the nuclear fission reactors, okay? So examples of fissile material, uranium-235, okay? When we say 235 is its atomic mass, okay? So there is uranium-238, which is naturally occurring, which is 99.3% of the uranium available on the Earth, okay? Uranium-235 is 0.7%. This uranium-238 is a fertile material. What does it mean? Is that it can't be used directly to create the splitting, okay? For all practical purposes, like I told, I'm oversimplifying the statement, okay? So uranium-238, when hit by a neutron, it absorbs a neutron, okay, for all practical purposes, for the energy band and the neutron spectrum energy, and it becomes a fissile material called plutonium-239, okay? So as you can see, uranium has several isotopes. So we understand what isotopes means, right? So the 235 is fissile, uranium-233 is fissile, whereas uranium-238 is fertile, okay? So this is how you classify this fissile and fertile material So fertile material is something which can be used to create fissile material. Okay, one of the most important fertile material for us is thorium-232. Okay, when I say all this number 232, 233, or so on, they're basically atomic mass. All right, because their atomic number won't change. It's only the atomic mass that is very important when it comes to the fission or fusion process. All right. So this thorium is available in plenty, most of the world. Okay, and this is the next, sought after material where this can be converted into a fissile material and power our energy requirements for several centuries and several millenniums. All right. Let's understand the concept of neutron cross-section and what neutron economics mean. Okay, what is neutron cross-section? Okay, so a neutron, when it is moving, okay, when it is ejected out in the process of splitting, fission process, this neutron, there is a finite probability of that interacting with the next fissile material. Okay, so let's take uranium-235 and it spontaneously fissions, let's say, and produces a neutron. That neutrons go and hit the other uranium atom, uranium-235 atom, okay, and that further splits into fission products and produce about 2.5 to 3 neutrons. Like I said, I'm oversimplifying the statement. So there is a huge probabilistic distribution of how many neutrons are produced for the process. So for all practical purpose, let's say about 2.5 to 3 neutrons are produced over the life cycle. So these 3 neutrons further interact with other fissile material, okay? And this chain reaction, this is called nuclear chain reaction, and this nuclear chain reaction propagates, okay? And to sustain this chain reaction, you need at least 1 neutron in the next generation, all right? So why, when there are 3 neutrons produced, why are we worried about it? Because what so happens that in the environment, this neutron can interact in several ways. It can create the fission, it can be absorbed so that it transmutates. What is transmutation? We'll talk about it slightly later from here, okay? Then it can be deflected, it can be lost, it can be absorbed by the moderator, it can be it might just die within its lifetime, or it might be absorbed by a coolant. So there can be any types of losses within the system. So this is called neutron economics. So we try to maintain the neutron economics so that the losses in the system is as minimum as possible, so that sustained chain reaction can be made, okay? This is very important. This is a chain reaction. Once you start, it keeps on going, and controlling the nuclear reactor so that you control the power, you control the activity, you control the way chain reaction sustains is very important. And that's what we term as neutron economics, okay? And while we are talking about neutron economics, while I spoke about different possibilities, probabilities that the interaction can happen, okay, this is all depending on energy and the material which is interacting with. And that in terms, in nuclear industry, it's called neutron cross-section, okay? Typically expressed in units called barns, okay? 10 power minus 28 meters square, okay? It's a cross-section area. So you're basically looking at the probability of this. So higher the absorption, the material characteristics, like I said, it depends on two factors. One is the material itself, their characteristics, and it depends on the energy of the neutron. So when we combine these two, it results in one single parameter known as cross-section, okay, barns, typically expressed in 10⁻⁻28 meters square. Okay, let's move on to the other concept, which is known as critical mass and criticality. You might read several of the articles where someone says that this particular nuclear reactor has gone critical. So it doesn't mean that it has been hospitalized or it is in grave threat or something. Criticality means that it has, it's a funny term that nuclear engineers used in the industry. So criticality means that, like in the previous section, we were talking about the term Neutron Economics. That means that the chain reactions is sustained. Okay, it has reached a stage where number of neutrons produced in the n+1th generation is at least one higher than the neutrons produced in nth generation. So that's how a sustained chain reaction is continued and criticality is obtained. Okay, that means it has started working and it has started producing power. Okay, so what is critical mass? So when you start a reactor or during the operation of the reactor, there is no stimulating, trigger that is done. To put it in another simple terms, for an inflammable item to catch fire, you need to ignite it, isn't it? That's how it continues the chemical reaction as long as the fuel is available. So borrowing the same concept, in nuclear industry, what happens is this fissile material needs to be in sufficient quantity that the chain reaction can sustain itself. It's a mathematical expression where you say that you have sufficient material that it can sustain the chain reaction by itself. If you have a system where it is lesser than the critical mass, it can't self-sustain the reaction. Okay, you need something to improve the neutron economics and sustain the chain reaction. Okay, so if it is able to sustain by itself, if you have got sufficient mass, it's called critical mass. And it depends on what kind of fission material, fissile material we're talking about. If it is uranium-235, it's one number. Uranium-233, it's one number. Okay, it's plutonium-239, it's another number. So for each fissile material, it has got its own critical mass. All right, it's a materialistic intrinsic property. All right, critical mass is an intrinsic property. Okay, so as we understood, so if we have the fissile material which is lesser than critical mass, it can't sustain the chain reaction by itself. So we need to engineer the process so that the chain reactions are sustained. That brings us to the concept of moderator. So moderator is a material or the environment that helps in maintaining the neutron economics, all right, so that the chain reactions is sustained. It's an engineered process through which you control the chain reaction. Typical moderators are heavy water, okay, graphite. There are several other gases, okay. So there are plenty of moderating materials that can be used for moderating the chain reaction where critical mass is lesser than, the fissile content is lesser than the critical mass. All right. So how it is different from control rod? What is control rod? So control rod is a material which is used to fine-tune the neutronic economics. What do you mean? It's kind of throttle of a motor car. Okay, so you can increase the speed and decrease the speed using the throttle of a motor car, isn't it? In the same way, using control rod, you can increase and decrease the reactivity. Reactivity basically means the difference of neutron availability from next generation to the previous generation. Okay, that's the reactivity. Okay, so using control rod, you can control the power that is being generated in the nuclear reactor. All right, typical example of control rod, boron, cadmium. Okay, there are plenty of materials which have got this control rod properties. All right, so what is that we are looking for in control rod in terms of physical principle? Control rod has large neutron section. Okay, neutron section, it has very large neutron section so that it can absorb. Basically, it eats the neutron. It takes away the neutron from the system. Okay, moderator, on the other hand, is a material which slows down the neutron. Okay, it slows down, it moderates. So when we say slows down, it means that the energy content of the neutron, okay, is basically moderated. That is hence the name moderator. Okay, so that is the purpose of moderator. Okay, in terms of physical principle. Okay, let's understand what is fission products. What are fission products? Transmutation and radioactivity. Fission products are basically the elements or basically the fragments that have been created after splitting a large atom. Okay, when large atom breaks, it breaks down into smaller fragments, and these fragments are called fission products. Okay. Transmutation. What is transmutation? Transmutation is a process where an element, you start with something. Let's say you start with uranium, but you end up with plutonium. You start with cobalt. You start with cobalt, you end up with nickel. Or you start with nickel, you end up with cobalt. Okay. You start with carbon, you end up with nitrogen. Okay. You start with hydrogen, you end up with helium. So transmutation is a process through which an element absorbs energy and becomes something else, or releases energy and becomes something else. Okay, when it absorbs and becomes something else, it's called transmutation. When it releases energy and becomes something else, it's called radioactivity. Okay, radioactivity is a natural process where it releases, an unstable atom. Okay, typically unstable because of its configuration of the nucleus. So spontaneously releases the energy into the surroundings and tries to obtain stabler configuration. Okay, this process of releasing the energy is called radioactivity. Okay, it can be in the form of releasing electron, releasing gamma radiation, releasing beta radiation, alpha radiation, any kind of process. Okay, these are the common process. So through which it releases energy to the surroundings and obtains a stabler configuration. All right. So with these fundamentals, let's look at the layout of the nuclear power plant. So what we are going to do here in this, while studying this layout, is we are looking at engineering the process so that we can extract power in a controlled way. All right, that's what we are trying to achieve here. Okay, so this typically is called containment building. Okay, and this particular building is called turbine building. Okay, and this, of course, is your cooling tower. Okay, these three, when you're passing by, you look at a picture of a nuclear reactor, you will see a dome like this, you will see a tower like this, and you will see a small building next to this. This is called turbine building. This is called containment building. So containment building, as the name implies, is used for containing the radiation so that it does not get released to the public domain. Okay, the purpose of this building is to contain the radioactivity or radiation activity within this particular capsule, and does not let it out to interact with the nature or public. Okay, so this typically contains primary containment and secondary containment. Primary containment, okay, typically it can be a steel structure or something like that, and there will be a secondary containment, typically a concrete structure, which is built so that, in case of breach in the primary containment, it still is contained within the secondary containment. So the entire engineering principle of the nuclear power plant is lying on the concept called defense in depth. Okay, there is always, it's like a fortress. If they breach, and designers think cynically, I may be a very optimistic person in life, but when it comes to nuclear design, I am the most cynical person you will ever meet. Okay, so we always assume that if things can fail, it will always fail. Okay, so what happens is, if the primary, like the fuel cladding, the fuel pellet itself, I'll talk about what pellets are in the next section. So fuel pellets itself is the primary containment, where the fission gas or the fission products are contained. Okay, in case that fails, then next comes the cladding, through which all the pellets are housed. Okay, if that fails, then you have the next system, which is the coolant system, which will take care of it. Like that, you have stages and various layers. Okay, like our skin, 7 layers of skin or something like that. So we have got layers of protection, so that the primary objective is the radiation or the radioactivity has to be contained within the system and should not be released out to the surrounding. Okay, that's the objective. And with that objective, this particular concept of containment building is, so you have control rods, which are basically controlled using mechanized process, and they are inserted and removed out as per the power demand. All right, and here is the fuel. Okay, when we say uranium fuel, it's not that it is used in the uranium form. The fuel can be of various types, which we will see in the later section. Okay, there are plenty of different types of uranium fuel. Okay, the reactor vessel, typically an engineering structure, a steel structure. All kinds of special steels and special materials are used in the nuclear power plant building. Okay, so many materials, wonderful quality control processes, and material testing processes are used to get the finest of the properties to achieve the engineering requirements. All right. This is quite trivial information, but however, I would like to explain. So the thermal energy which is produced here in this reactor vessel will be absorbed carried by this primary circuit, and that will exchange the heat with the secondary circuit, and that thermal energy will be converted into mechanical energy here, and that will be spent through the generator and converted to electrical energy, and which will be passed on through series of electrical transformation and supplied to the grid. All right, so this is how the nuclear power plant layout looks like. Okay, I'll head on to the next one. Okay, so types of nuclear reactors. So the types of nuclear reactors can be classified based on different classification: neutron energy, moderator, coolant, fuel, and generation. So based on neutron energy, let's say we have got thermal neutrons and fast neutrons. Okay, so fast breeder reactors, okay, typically liquid sodium cooled or something like that. So fast breeder reactors and thermal reactors. So thermal reactors, you have got pressurized water reactor, BWRs, you have got gas reactors and all kinds of things, okay, which uses the principle of thermal energy of the neutrons. And the other one is fast neutrons, moderator. So you can use heavy water, which is basically deuterium oxide. You can use graphite. You can use various other, moderators for slowing down. Okay. So for fast spreader reactors, you don't need moderator because, it happens in the fast spectrum of energy. Okay? Coolant. So you can use light water, you can use heavy water, you can use liquid metal, you can use molten salts, you can use gaseous, all kinds of materials can be used for extracting the thermal energy from the primary process, which is called coolant. Okay, so based on coolant, you can classify different types of nuclear reactors. Fuel, so uranium dioxide pellets, okay, uranium carbide, metallic fuel, you can have dispersion type of fuel, sandwiched fuel, so all kinds of material. And also it can be in the form factor, whether it is a plate type, whether it's a cylinder, whether it is a bundle, whether it is aqueous, okay, whether it is heterogeneous, whether it is homogeneous. So based on different types, how fuel can be used, it can be used. Even gaseous fuel is the latest concept that is being worked on, where it can be directly used as uranium fluoride. Okay, and it has got great potential when it comes to the energy density, and especially for the space exploration projects. Okay, and with respect to generation means not production. Basically, generation is basically as in version. Okay, so generation 1, generation 2, generation 3, generation 3 plus, generation 4, which is still under design. None of them are in operation. And then there is generation 5 as well, which is also in the conceptual stage. Okay, so let me move on. So what are the spin-offs of the nuclear technology? Medicine. Okay, very quickly you can easily tell that medicine in the form of X-ray, okay, bone marrow, X-ray, general X-ray, and cancer treatment, all that medicine, medicinal purposes, you need nuclear technology. Cesium-137 is not naturally occurring material, cobalt-60, so they are not naturally occurring, so they are used for cancer treatment and all other purposes. Agricultural seeds, so to aid the germination of seeds and increase the shelf life of seeds, these seeds are irradiated by either gamma, electron, all kinds of radiation technology through which the germination of seeds can be promulgated in agricultural industry. When it comes to food and dairy, for food preservation, avoiding wastage of food, increasing the shelf life of food and dairy products, again, irradiation can be used. Material research, okay, what happens to the material when it goes to the space? We don't know, but we can simulate it here using the nuclear reactors, put the material, give it a certain dose and see what happens to it. Okay, that way, it helps material research. Security, your smoke alarms have americium 104, which is used for ionization, so that smoke can be detected earlier. Okay, environmental research, okay, carbon dating, water availability, oil exploration, it can be used. Manufacturing purposes, several materials can be synthesized and produced. Space exploration, I spoke about uranium fluoride system and all that can be used in space exploration. So whenever you are having a space exploration and there is no, you are on the darker side of the planet, so you can use nuclear propulsion to do that. Okay, the secondary application, you can use it for hydrogen production, okay, desalination, okay, you can use it for the exclusion zone, can be used for solar thermal, solar voltaic plants, atomic battery or nuclear battery. The waste products can be used for generating heat. The fuel for fusion, tritium, which is produced, is a very important fuel for the nuclear fusion. Okay, so I'll cover a few of the misconceptions what nuclear energy is in the public domain. Okay, so many people think that nuclear means weapon of mass destruction. Sorry, I tend to disagree. Nuclear, to me and to most of the people who are working in the nuclear industry, it's for purely for peaceful purposes. And if it is assumed to be a bomb or weapon of mass destruction, maybe that can destroy only poverty, energy insecurity, food insecurity and all that. So it is a weapon against poverty. It is weapon against hunger. It is weapon against energy insecurity. But when it comes to mass destruction, no, it's not. Okay. It's dirty. No, it's one of the cleanest fuel available on Earth, because in the operation, as you have seen, it does not release carbon dioxide at all. Okay, or any of the greenhouse gases. So that way, it is one of the cleanest energy generating process on Earth. Okay, radiation exposure to public. This is something which I would like to tell. So there are concepts called radiation activity, which is measured in becquerel, and exposure. So how much ionization it causes in a kg of a material, and how much dose it is absorbed, like how much energy is deposited, so many joules in kg of material, that is absorbed dose, equivalent dose, and effective dose. Okay, equivalent dose is basically how much my eyes can resist, how much my nose can resist, how much my skin can resist, like that. And effective dose is overall effective dose that has been dissipated in the body. We will see that in detail later. Okay, it's basically quite safe. So safety operation, yes, one of the safest thing we will see in the subsequent slide. Waste disposal, there are long-term solutions. It's a misconception that it produces lots of radiation waste, radioactivity waste, which cannot be managed. No, it's not, because it's renewable. By definition, nuclear energy is renewable. So whatever is the fission product, that can be further recycled and made into a fissile product again and can be used. Okay, the amount of fissile that is generated can power for several hundreds of years, or for several generations of human generation. Okay, world is denuclearing, so it's not. There are few reactors that have been pulled down for the reason that they're old and vulnerable. Older generation, they are being replaced by newer generation. Okay, there has been constant addition of reactors all over the world. So world is nuclearing. Like I said, that is the largest known energy source on Earth, cleanest and largest. Okay, so with respect to the safety of operation, as you can see, these are number of deaths that have happened during the operation of a lifetime of a brown coal operation. Look at the numbers in nuclear. The number is so less compared to the coal. So this is quite safe. Okay, let's look at so Radiation Safety Act 2016 Schedule 3, which is set aside by the New Zealand legislation, which prescribes the effective dose limit for public, okay, from the radiation activity of a reactor. Okay, reactor or any other source is 1 millisievert per year. Okay, please pay attention to this number, 1 millisievert. Okay, and as per the survey, the average effective dose, the background dose that New Zealand people receive is 1.8, which is 80% higher than what is prescribed for public as per the legislation. So the background radiation is so high. In fact, if you have a cross-country flight, okay, if you travel from one country to other, let's say New Zealand to Australia or any other place, you will receive effective dose of 200 times higher than this permissible limit of 1 millisievert. All right. So when the background radiation you absorb is so high compared to what the during operation you receive, then terming it as it releases radiation, I think is quite unfair. It is beyond facts. Okay. Let's very quickly understand the fusion process. So it works on the same principle, binding energy. So when two masses are joined, the final product mass is slightly lesser than the initial mass of the constituents. So this difference is called the energy that we use as a thermal energy. All right. So we are slightly short of time, so I'll quickly run through. So the fusion can typically happen in two chains, proton-proton chain or carbon-nitrogen-oxygen cycle. So for the size of sun, typically proton-proton chain reaction is used. Anything more than the size of sun, okay, typically CNO, carbon-nitrogen-oxygen cycle is used. Okay, so these are the two known phenomena right now. There are plenty of phenomena that is ongoing and it is in research stage, but these are the known discoveries as of now. Okay, then we will just look at Lawson criterion very quickly. Lawson criterion is basically the net energy produced by a fusion reaction so that the losses are lesser compared to the generated. Okay, this is very important for design of a fusion reactor. Okay, so there are different types of fusion technology. Thermonuclear, inertial confinement. So you confine it in a small space using pressure and heat, you fuse them. Thermonuclear, you create plasma and confine in a magnetic field. And beam target, using accelerators, using high energy kinetic energy, you bombard and beam or beam target, one moving, other stationary, and you create. Hybrid nuclear, create initial energy by fission and then fusion, or fusion, explode a bomb in a controlled way and then use the fusion. So fission fusion, or fusion fusion. Okay, bubble fusion, this is one of the beautiful technology which works on sonic cavitation. So that's how the fusion technology can be sustained. So let's understand what climate change is. Climate change refers to long-term shifts in temperatures and weather patterns. And these shifts may be natural, but since 1800s, anthropology, that is human activities, have been the main driver of climate change, primarily due to the burning of fossil fuels like coal, oil, and gas, which produces heat-trapping gases. So this is the definition given by UN. So this is what climate change means. Okay, so what is greenhouse effect? Greenhouse gas, the gases which trap the energy so that, whenever the sun's energy hits the earth, it reflects back. While it reflects back, some of the energy is absorbed and it does not dissipate the entire energy into the space. So because of that, this energy is trapped and that increases the, the average temperature of the earth. And this is called greenhouse gas. And this is expressed basically in global warming potential. So carbon dioxide is taken as 1, for methane, which is 27.8. So for different gases, there are different GWP, that is global warming potential. And through that, it's what is carbon footprint? For every process, you add to the carbon dioxide directly or indirectly. So we might assume that for nuclear industry, because it is not producing carbon dioxide, it's basically a carbon neutral. No, it's not, because during the construction, during the operations, during many processes, okay, we have invested carbon in, that creates certain carbon footprint. Okay, so we will look at a few of the aspects there. Okay, so as you can see, this is basically life cycle greenhouse, or also known as emission intensity. So how much greenhouse gases, carbon dioxide equivalent for every kilowatt hour, okay, energy produced. Okay, so kilowatt is power, kilowatt hour is energy. So for energy, each kilowatt hour of energy, how much grams of carbon dioxide equivalent is produced? As you can see, for different for coal, especially it is 1000 units, 1000 grams, basically 1 kg, but nuclear it's about 60. Okay, this is a probabilistic distribution. Very quickly, I'll go to the next one. So this is another survey by IPCC, means Intergovernmental Panel for Climate Change. That working group 3 has produced these results in 2014, which says 12 units of carbon dioxide equivalent is released compared to coal of 820. Okay, and you can see it is in comparison to hydro and solar, it's much better. Okay, now look at one of the latest paper. This is in March 2022, where French nuclear agency has released this number, which is 3.7. So less than 4 grams, not even 12, not even 12. It's basically 3.7. That is the number which they're giving. So there are plenty of agencies which report different numbers. Like I would like to borrow the words of Winston Churchill. If two people agree on everything, then the second person is irrelevant. Okay, so that way we have to look at it, these stats that different agencies have different numbers, but you always collect the numbers from the horse's mouth. So I'm collecting this information from the French atomic energy agencies. Okay, so this is the concept of what is known as levelized cost of energy. Okay, so what happens is you levelize based on different parameters. So nuclear is quite competitive. That's the take away from this slide. Okay, so let's talk of sustainability paradox and sustainability trap before we close the session. So typically what happens is sustainability, by definition, you are looking at the future. Okay, but the energy security is the present problem. So if you want to solve something in the future, you land up not catering to the present. And that is known as sustainability paradox, which I'm currently working on this particular terminology, and I'm producing a paper. Very soon it will be published. And I'm also like, I would also like to introduce a concept called sustainability trap, where what happens is if we have this is called low relevance and high relevance. And this is basically low alignment and high alignment. So if you have got something which has got high alignment and basically low relevance, then you are basically getting into the trap of sustainability. That means that you are spending more than what you are getting. Okay, and that can be a disaster from economics point of view. Okay, if you do PEST analysis, which is a political, economical, culture, socio-cultural and technological analysis of any particular a process, then you will always end up with having a sustainability trap where it is having high alignment and low relevance, and which is where many of the upcoming technologies like offshore wind, onshore wind, there are certain technology which can lead to sustainability trap. Okay, looks very aligned, but it is a trap. Okay, it's a financial trap. Okay, so I'll as discussed, our target is to limit this temperature rise to 1.5 degrees as per the Paris Agreement. And as you can see from 2000, 33 billion tons of billion tons of carbon dioxide has been added since 2000 in the energy sector itself, which is a question. So why not look at nuclear? Okay, and nuclear prevents the release of about 2 billion tons of carbon dioxide each year. And so far, in past 50 years, nuclear industry has offset the carbon emission by 55 gigatons. Okay, so let's look at the bigger picture. So what we are talking about is this. So low emission intensity, as you can see, the entire life cycle, it's less than 4 grams of carbon dioxide that is produced for each kilowatt hour. Continuous and controllable. So unlike other renewable sources, this is continuous and controllable. Okay, we have engineered the process to control it. Okay, we are not leaving it to nature to control, but we have engineered the process. Economical, from operations point of view, we have seen the IPCC publication on what is known as the LCOE. Okay, and infrastructure change, it demands very little infrastructure change. Okay, immediate impact, yes. This is where I really like this nuclear technology, because I think this is the future that needs to be adopted immediately, because this is established. Okay, in next 100 years, if we can control the carbon dioxide emission and also simultaneously secure our energy needs, then probably at some stage where we have taken care of the energy needs, we have taken care of the immediate effect, then we can slowly denuclearize ourselves and simultaneously explore other technology. So that is where nuclear technology being established, proven for past 50 years, it can be very prudent to adopt it on high scale and immediately address the problem of 1.5 degrees, limiting to 1.5 degrees. Okay. And we have seen that it fuels the other technologies and spin-offs like hydrogen production. It, produces tritium, which can be used in fusion reactors. So like that, it fuels the other technologies and also produces several spin-offs which can be used for societal purposes. Okay. So with this, I'm closing the presentation. I would like to say thank you to everyone who attended. And I would also like to thank all my teachers who have helped me to get here, and also like to thank SIGI, my colleagues in SIGI who have helped me, always constantly supporting me in producing this presentation to you. All right. Great. If you've got any questions, please shoot in Q&A. Currently, I don't see any questions. Would you, if there are any pressing questions that you have with respect to policies, with respect to climate change accounting, carbon accounting, any questions with respect to other technologies of fission and fusion, please feel free to ask.
Thank you, Vinay. While we're waiting for some questions to come through, I'd like to obviously thank you for taking the time to present to the group as well. But in the meantime, perhaps we can do a little plug for the upcoming SIGI conference, which is happening at the beginning of October of this year in Auckland. For those who haven't seen it, we will be sharing some more information to SIGI members, or you can head to the SIGI website. Abstracts have now closed for the conference, but we are taking registrations as well as dinner registrations to join other SIGI members and the committee at a fine dining experience dinner as well. So please, if you haven't seen that, head over to the website and have a look. I've just seen a question come through. So is there a solution to the long-term waste disposal if no more nuclear reactors are brought on the line?
That's a great question, Ben. That's a wonderful question. Yes, long-term waste disposal, there are several strategies that all over the world that is being adopted. Let's understand it this way. There are two cycles of nuclear fuel. One is called open cycle, other one is called closed cycle. Closed cycle is basically something known as circular economy. Okay, whatever is the nuclear waste that is produced, it will be reprocessed. Of course, you will spend little more carbon footprint out there. You'll spend your carbon credit there. But once that is processed, that will be a grade 1 fuel again, which will go back into the new reactors. Okay, so which can be coupled with the fresh fuel. There are strategies through which it can be balanced. And typically the engineered process for this is the fuel that is spent, it's called spent fuel, will spend a lot of time where the radioactivity is made as low as possible in a pool of water, and there are different strategies like that, technological solutions like that. And by the time it is shielded in form of a canisters and stored somewhere, the radiation release is so less compared to the natural sources. Like, when you eat a banana, there is potassium 40, which is naturally present there, which is radioactive. So there are plenty of things that happen in the nature, the background radiation. So it will be much lesser than the background radiation. So that's how there are long-term waste disposal strategies available, which can be done. Great question. And we got another question which by Enrique. What's the position of New Zealand about adopting nuclear power plants in the future? In New Zealand, I believe it is strictly anti-nuclear. So that they have it's basically a policy decision. So yeah, but there are always options open. the good news for New Zealand is probably New Zealand is one among the very few countries in the world where the renewable energy contribution to the energy security is higher than 50%. Maybe one among the 12 countries in the whole world. Okay. And typically in New Zealand, 76% of energy is coming from renewable. Okay. And the energy insecurity problem is not really very high. So from those consideration, nuclear is not very prudent because that might lead to what is known as sustainability trap when it comes to New Zealand. Okay. So I think nuclear is not, it may be an overkill when it comes to technological solution. Okay. Let's move on to the other question. Thanks for the interesting talk. My understanding is that the #1 greenhouse gas is water vapor, which is primary output from nuclear. When this is taken into account, is still better than gas, etc., for climate change? Yes, it's a great question, James. Yes, clouds and water vapor is also one of the greenhouse gases. Okay, it also produces equivalent carbon dioxide effect. Okay, and that is the natural process also which happens. Okay, but rather than having methane emission, chlorofluoro emissions, or carbon dioxide, this water stream is greener greenhouse, basically. Okay, kind of healthier option, rather less evil compared to the other evils present. So if you have to choose between lesser poison compared to the bigger poisons, this is a better poison. Okay. So that's a very great question. Yes, it's debatable, but among all the options, this seems to be a good option. Okay. Okay. And other question by Zhang Tang. How long do you think the human being can have the first commercial fusion power station? This is a question which scientists want to answer yesterday. Okay. So as a child, I have also heard that, the fusion is ready. It is going to come out in next 10 years. And that somehow has been consistently maintained in the industry. Even after 35, 40 years, they are still saying the same. Jokes apart, nuclear fusion recently has hit milestones, great milestones, where we are able to sustain the confinement time, very high confinement time. So which is a great output. So what happens is that any new technology, it takes its own time. So as you can see, fusion is not ready yet, but if we are successful, that will solve all our future problems. That's what at least we like to believe and hope for. Devil is in the details. We don't know what the problems and challenges that comes and posed in the future. But currently, scientists believe, engineers believe that that is the most promising technology that can fuel our future. Okay, so thank you. And yeah, Ben again has asked a question. Are there benefits of using micronuclear reactors over the larger traditional nuclear power plants? Excellent question. Yes, Ben, I forgot to mention this. Thanks for reminding. In the generation 3+ and generation 4 reactors, there is a concept called small modular reactors, SMRs. Okay, these small modular reactors are considerably very small compared to the traditional size of the power plants in generation 2. So it brings down the exclusion zone, it brings down the land footprint. Okay, like carbon footprint, land footprint, it reduces the land footprint, it reduces the water footprint. Okay, and they are quite modular in nature. That's why it's called small modular reactor. So they're so modular in nature that you can take out certain things and put some things, and it can be easily controlled, and they're so small. And there are also plans of generation 5 reactors where it could be the size of a button cell. Okay, we are getting there eventually. So atomic battery is quite different, which uses only the radioactivity. It's basically the radioactivity, not the fission process that happens there. So the energy released is because of the radioactivity of the fission products. So the reactor of the button size cell is about to be there. There are experiments and development across the globe that is happening, where we are looking at wonderful technological solutions which can make things much more beautiful. All right. So lovely. So thank you very much for everyone to join. And I would like to reiterate what Holly just mentioned. So on October 7th, Friday, SIGI is organizing a beautiful conference at Becca, Auckland. I request all of you, if you have not registered to that program, please register. The abstract has been unfortunately closed, but you are free to register for the program and also for the dinner event, so that you can meet and interact with several of the wonderful immigrant engineers across New Zealand and support each other. All right. So thank you, everyone, for joining me. Over to you, Holly. Thank you.